Manav here. Let me know if you are able to see me and let me know if you are able to hear me. Good morning, everyone. So, give me a quick good morning in the chat window to let me know if you are able to hear us clearly. What we want to ensure is that, given that a huge number of you are already here and have joined, we want to make the session as good as possible, as interactive as possible, and as purposeful as possible for you. The way we will do today's session is I have Dipanjan with me, who is one of the leading voices in data science in India. And I'll want Dipanjan to introduce himself, talk a little bit about the topic. But what we would want to do, Dipanjan, with you is that we would want to field a lot of questions for you. Yeah. So, Dipanjan, everyone has prepared some content also that he will present on deep learning for, let's say, 25-30 minutes. And after that, we'll open up for Q&A, and I would pick questions from the chat window and ask Dipanjan. As you would see that the number of questions that come usually is huge. So my apologies in advance if I'm not able to take all the questions. You can always email us later at academics@insaid.co if you have questions that get unanswered, right? But what we'll try to do is take the most important questions, right? So Dipanjan, welcome to the session. And first of all, thank you so much for being with us on a Sunday morning.
No problem. Thanks for having me.
All right. So Dipanjan, before we get started with the session, I would love you to introduce yourself and talk a little bit about how did you get into the field of data science and some of the recent accomplishments. That would be great.
Sure, sounds great. So, hi everyone. Thanks for joining in. Yeah, basically, I've been working in this field for over 8 years now, professionally, and I got started because during my bachelor's and master's, I was very interested in areas related to extracting insights from data. And that time, again, data science was not as hyped up as it is right now, but it was purely an interest from working with computers and then working with data, and then basically I started my journey as a data scientist, and I worked with different companies, including Fortune 500 companies like Intel, Red Hat, IBM. I also have been working as a data science lead at Applied Materials. And besides that, I like sharing my knowledge with the community. So I've done that in various ways in the form of events, conferences, workshops, as well as articles and tutorials. And I do that regularly, even now, in different events across the globe. And yeah, besides that, I also work as a consultant and basically work with different startups as well as large scale companies in terms of upskilling people, as well as organizations and AI initiatives in terms of training, as well as basically seeing how we can turn an idea into reality. So that is basically where we work on proof of concepts and see how they can basically become tangible and usable in the long term. So yeah, that's a bit about myself.
Awesome. Great intro, Dipanjan. One of the questions, Dipanjan, that since we are one of the largest institutions in this space in India, that students ask us is that there is so much, this field is never ending, especially from a newbie's point of view. What was your journey like? What did you start with? And over a period of time, what layers did you keep on adding to your skill set?
Sure. So in general, as it typically happens, like you need to start with the fundamentals in terms of understanding how can you basically learn this new paradigm, which is very different from traditional programming, where you have to code your logic and build your software. This is more in terms of how can you enable insights from data. So the first place where you need to start with is to understand what kind of data is there and how can you process it, how can you clean it, how can you visualize it. So the fundamentals of basic data understanding, processing, and once you start getting there, you need to dive into some aspects of statistics, data visualization, and then you go forward in terms of one step advanced, where you go into machine learning, understand the the fundamentals of machine learning, as well as follow a practical approach of understanding how can you apply machine learning models in real world scenarios. So that is where there are a wide variety of data sets and problems out there. So not just about learning or watching a video or a session, but also going out there and trying it out yourself, no matter how small the problem, because you need to start somewhere. And then from there, I basically started diving into the newer areas as they started becoming more relevant in the industry, like deep learning and also computer vision and natural language processing. Many people might say that you need to specialize in one domain and stick to it, but it depends on every person, honestly. From my perspective, a breadth of skills is also very relevant, because then I can target any company. And especially if you're working as a consultant, you can work with different domains, which is always useful. But that's where also, I mean, your knowledge shouldn't be very shallow. You should know essentials as well as how you can apply it and solve it, be it what any problem which you're tackling. So for me, it was basically starting with the fundamentals and then picking up one new thing at a time in terms of how much relevant it was in the industry. Like, and the other things, I mean, I just keep a track of it. And whenever I know that this is when I really need to dive into it, I dive into it. Like, let's take reinforcement learning, for instance. I know what is out there, what are the essentials, but I have never dived too much from an implementation perspective, because it's still not as much relevant in the industry. I would say less than 5% of use cases are being used in the industry for reinforcement learning. And again, I mean, building gaming simulators and all that is fine, but in the industry now we are seeing, like, let's say in finance, in trading and manufacturing, we are seeing some applications of reinforcement learning. But maybe once it becomes more prominent, I will again dive into it, because time is the most important thing. So yeah.
Yeah. And I think, what you rightly mentioned is that you need to build certain depths in each one of the topics, step by step, but you also need to taste all the topics, because you never know what your inclination, or for example, a lot of time we have these apprehensions. For example, computer vision is going to be difficult. You never know, you might end up wanting to spend your entire life on computer vision. And that's why tasting all of these different areas is important. Yeah.
Absolutely.
So my question to you is that out of all the different areas that you have tasted now in the field of data science and AI, what tasted the best for you? What are the areas that you really feel passionate about, from where you feel that you can go deeper and deeper and deeper, and it's like never ending?
I think definitely deep learning itself holds a lot of promise, because it was hyped up for a long time, but now industry is actually leveraging it in different domains. And the depths of deep learning itself is endless. Nowadays, we are seeing things in like aspects like self-supervised learning, which is like, without a lot of label data, how can you still get a better performing model? So I think with deep learning, it's endless. And the best part is, if you're solving problems in computer vision or natural language processing, you can solve a lot of them with deep learning. And you can go really deep in terms of the research which is coming up nowadays, be it transformers, be it self-supervised learning in terms of some of the latest architectures which have come out recently from Facebook, Google, and so on. So I think essentially all the fundamental concepts which you learn, we are seeing some form of it come back in some way or the other, be it in the form of semi-supervised learning or unsupervised learning in the context of deep learning. So from a technical perspective, I would say deep learning and transfer learning definitely are areas which are personally something which I like, because there is no end to seeing like how it's evolving over time. And again,
Uh,
I definitely would say there is a lot for even me to learn, and every day I'm learning something or the other. Yeah.
Awesome. Great. So how about we dive into the presentation that you have, and for everyone, this industry talk is also being broadcasted on YouTube. So this will be later available on YouTube as well, and I think we have a good number of participants right now joining on YouTube as well. So later, if you want to refer to any section, it's available on YouTube. I'll just show you the playlist also. It will be categorized in this playlist, data science and AI industry speaker series. Let me ask a quick question to the Insaid community. All the students, have you all gone through all the videos in this playlist? Because you might not have attended some of these sessions, but it is incredibly important that every speaker brings, for example, Dipanjan today is going to talk about some aspects. What you would want is, and that Dipanjan has also mentioned, get perspective about small areas also. And from each industry speaker session, even if you can get one new idea, big idea that you can think about, I think it would be worth watching that content. So Dipanjan, over to you, and I would love for you to share the material that you have and talk about deep learning. So far, Dipanjan, just to discuss a bit, most of the speaker sessions we have done have been around data visualization, data storytelling. They have been about framing a business problem into a data science problem, but very few we have done around deep learning. So it will be a fantastic new discovery into this fascinating world. So over to you, Dipanjan.
Sounds great. I will share my presentation. I think the context is good because I will basically be covering about how can you understand some of the fundamentals of deep learning, as well as how can you basically see some real world use cases which have been solved using deep learning. So let me know if you can. I'll just share my presentation. I will just hide this for now. I hope the presentation is visible, right?
Yes, we can see the presentation, Dipanjan.
Okay, great. So today I'll be talking more about why is deep learning becoming more relevant and more important in the industry. And I will be covering some of these main areas, as you can see, in terms of what do we mean by learning before we dive into deep learning. That is an important thing. And then I will also be talking about why is deep learning effective, a brief about transfer learning, since it is very relevant in the context of deep learning, some of the most popular deep learning model architectures which you will typically be needing whenever you are solving, let's say, 80 to 90% of the problems in the industry. These are the models which you will come across for sure. And then I will showcase in terms of some of the essentials of diverse problems in the industry which have been solved with deep learning and are still being solved in terms of data center device failures in infrastructure. Malaria detection is healthcare. Security vulnerability detection is in cybersecurity. Image super resolution neural style transfer is all around visual projects. So let's dive into it. I think I've already introduced myself, so I won't spend too much time. But like I said, I have been working as a data science lead. I've published several books, and I work with different companies and startups across the globe in terms of initiatives in data science and artificial intelligence. So let's understand about the basics of learning. So as I was saying before in our discussion, that the whole point of this field of AI and data science exploding is because this is a new paradigm where the idea is to build applications which can easily solve complex problems, which are not sometimes difficult to solve as a human, but it is difficult for a human to solve it at scale. So that is where nowadays we are diving into data driven paradigm of programming, where instead of traditional programming where we already have some inputs and we have some kind of fixed rules, like let's say a program to compute tax. So there are some fixed rules and you code the solution and then you deploy it. But there are increasingly complex problems which have come out nowadays in terms of image recognition, object detection, speech recognition, text to speech, speech to text, language translation, which are very difficult to solve using hard coded rules. And that is where making machines learn from this data is the whole data driven paradigm. And we have seen increasing success of multi-layered neural networks to solve these problems. And that is where, again, this is a very cliche slide, which you probably have seen a lot of times. But the reason for putting this forward is so you get the context of deep learning before we dive into it, in terms of, again, AI is a very misused word, but in my, at least from my perspective, an AI system is basically any kind of an intelligence system which can solve a human level intelligence task in terms of being able to perform a complex task, being able to comprehend and understand the data given to it, and then predicting or giving us some kind of insights. And the way these AI systems are powered is by leveraging machine learning models or deep learning models, which increasingly find different kinds of patterns from the data you feed into it. So the more data and also the right data you feed into it, the better performing the model is. And the other perspective is deep learning is a subfield of machine learning. So the training process and everything is very similar. There is no difference. The main perspective here is that the architecture of deep learning models is based on complex multi-layered neural networks, and they tend to scale with bigger and better data sets. And in terms of the types of learning, I think all of you are aware about this. We have supervised learning where you deal with some kind of historic label data to train the model, like a house price prediction based on different features of the house, like square feet, number of rooms. And you have unsupervised learning where you have a high level goal in mind. And the idea is to achieve that goal to an extent based on a lot of data which is available to you, but that is not labeled. So this could involve finding out similarities, recommendations, or let's say clusters or groups of similar entities. The classic example is customer segmentation, where we try to find out which are maybe my most loyal customers in an e-commerce store. And the last one is reinforcement learning, which is more dynamic in nature, where the whole idea is to train an agent to perceive the environment around it and achieve a goal again based on learning from its mistakes as well as making the right decisions where it gets rewards. Now, coming to neural networks, the inspiration for neural networks has been from the human brain. The idea is how close can we get to the human brain? But the thing to remember again here is neural networks is not the replacement method for a human brain. We are still nowhere close to figuring out how the human brain works, but you can say this is like a first or a second step towards getting there. And a human brain is consisting of a lot of neurons, which basically perceive what you're viewing, smelling, touching, and there are electrochemical impulses which are carried out from one neuron to another neuron till, let's say, you move your hand or you're able to perceive or smell something and so on. So everything is tied to the brain. So similarly here, whatever is being perceived is basically presented in the form of inputs. This is a structure known as a neuron, also known as a unit. And typically in a neural network, you have these things known as hidden layers, and each layer consists of hundreds or thousands of these neurons. So a single neuron is something which receives inputs. These inputs will also have some kind of importance attached to it that is known as weights. And then inside the neuron, you will have a linear approximation and a computation happening, which is basically multiplying all the weights by the inputs and adding a bias to it. And then the innovative part of neural networks is it is not just a linear function, but you apply a nonlinear activation function on top of it. This nonlinear activation function serves as a purpose to basically, you can think of it like fire this neuron, just like human brain neurons are fired based on some kind of inputs coming into it. So that is where the nonlinear activation function helps in firing or not firing these neurons so that the information is propagated further through the network till some kind of a response is generated. And here, these weights are learnable. So these weights are trained by making the model better and better by reducing the error which is generated when the model is making predictions. So these are the basic structures of neural networks. And in terms of training for neural networks, so probably some of you already know about this, or you will be learning about this. So the whole point of neural network training is you usually start off with some kind of a label data. Even if your data is not labeled, you get it into that kind of a form. Like, let's say, a source image which is noisy and a target image which may not be noisy. So you generate your data to basically have those pairs of X and Y. You forward your X or your features through the network, which consists of multiple layers with neurons and weights in each of those neurons, and you generate some predictions. And your initial predictions will be really bad, let's say. So you will compare your predicted values with the actual values, and you will find out what is the loss based on some kind of loss functions, like a mean square error or a cross entropy loss. And then you will do differential calculus to find out the gradient of the loss with respect to each and every layer from the back to the front of the network. And that is why it's known as backpropagation, because you compute the gradient of the loss, you update the weights of each and every layer from the back to the front. And that is known as the process of backpropagation, where you keep updating those weights, like I said, those importances or weights for the connections in each and every layer and in each and every neuron till you start reducing the error. So basically, you pass this data multiple times through the network known as a forward pass and backpropagate the errors till your loss reduces to some extent, and it's known as convergence. So that's like a high level process of how neural networks are trained. And in short, deep learning can be called as machine learning on steroids because essentially it can help you in do a lot of things like automated feature extraction, as well as downstream problems like classification, regression, detection, segmentation, and so on. But in case of traditional machine learning, often you have to manually extract features. Like if you are dealing with computer vision problems, you have to sit and extract features like edges, corners, features based on descriptors like surf, sift, and so on. But in case of deep learning, a ConvNet can automatically extract most of the relevant features for you. And in terms of the terminology, so what is deep neural network? So again, this is heavily debated, but anything having more than 3 to 5 hidden layers is usually termed as a deep network. Otherwise, it's termed as a shallow neural network. And now, why are we talking so much about deep learning? Why is it so effective nowadays? So, if you look at this slide, it kind of gives you that perspective that the adoption of deep learning across different sectors in the industry have been massive, starting from consumers, where you have digital assistants, personalized search results, chatbots, AR, augmented reality, virtual reality. All of this is being powered by some form of deep learning or sometimes multiple models together. In healthcare, drug discovery is being powered by deep learning as well as a combination of reinforcement learning. You have other medical imaging based use cases like cancer detection, diabetes detection, figuring out which part of the image is basically localizing the issue or the problem a person is facing. So that's like segmentation. So a lot of work is being done in healthcare. In finance, I briefly mentioned, so deep reinforcement learning is being used in algorithmic trading, and you have other problems like risk detection, fraud detection, and nowadays even we are seeing the use of generative adversarial networks, which are being leveraged to see how we can generate more data also in case we have less data. In retail and e-commerce, again, I mean, this is where you have recommender systems being powered by deep learning. You have supply chain, logistics, transportation. So basically, the whole ecosystem around retail is being supported by deep learning in some way or the other. Let's take, for example, in case of inventory management. Nowadays, we are seeing drones which are actually taking pictures of shelves and saying whether you are running out of some kind of an item, or even taking the labels of packages and automatically extracting the quantity, the serial number, and tracking all of this using digital mechanisms. Government themselves are investing heavily in these kind of methods in the form of smarter cities, which use a combination of machine learning, deep learning, Internet of Things, edge devices. And basically, the scope is endless. Even in traditional industries like oil and gas, we are actually seeing innovative approaches of deep learning, where we are seeing methods being used to figure out when should an oil well drilling be stopped so that you don't end up ruining whatever has been drilled so far. You don't end up ruining the equipment. So people are actually profiling the whole soil and then trying to figure out when they should stop drilling. So definitely innovative areas of exploration being happening in terms of deep learning methods and actually implementing them in the real world. And also transportation, again, we know about self-driving cars. Nowadays, we are seeing also like automated logistics and transportation in the form of automated trucking. So companies are investing heavily. Companies like Tesla trying to reach that level 5 autonomy, which is like full scale autonomy. I think right now we're at level 3 to an extent where you have to take some of the most critical decisions. But again, we are trying to get there. And like I said, a lot of applications in traditional industrial aspects like factory automation, smart factories. And that is what will take us basically to that industry 4.0, where you can have a factory which automatically runs by itself with minimal human supervision because it will figure out what is going to be the optimal yield. When can a system go down, which I will talk about today from an infrastructure perspective. predictive maintenance, preventive maintenance, precision agriculture. So a lot of places we are seeing increasingly that the more data you get, the better you can leverage that data and extract insights from it to prevent failures, to automate things to run faster, as well as get rid of unnecessary manual tasks so that you can focus more on solving problems to reach better efficiency, get a better revenue, and so on. And in terms of other industries, advertising, education, gaming, obviously IT services, space exploration. So the possibilities are endless, and we are even seeing areas which previously didn't use that much of, let's say, data science to an extent, except let's say traditional data analysis, like in sports. Obviously, there was some form of business intelligence being used by basic dashboards and Excel sheets. But nowadays, we are seeing sports analytics emerging as a mainstream field where people are actually capturing videos of entire matches to figure out strategies of their opposing team and then leverage deep learning as well as reinforcement learning models to build some kind of strategies and extract insights. And we are even seeing startups and companies who are providing these services nowadays and even charging good money for it. And like I said, why is deep learning becoming effective? Because it saves you time. With a lot of complex problems, you will be focusing more on trying to understand the problem and solve it in the right way. So, especially with areas like unstructured data, video, audio, image, text, deep learning models can automatically help you extract the right features instead of you sitting and manually extracting features. And of course, it can help you with solving the downstream problem also, like classification, segmentation, and so on. And because a deep learning network is a hierarchical structure with multiple layers stacked one on top of the other, each of these layers have some kind of a role to play in terms of extracting some generic features like edges, corners, as well as stacking them on top of each other and extracting further more complex and specific features from them, like understanding how does a nose, how can you represent the nose, eyes, and even complete facial structures. So in this way, because of its automated feature extraction as well as learning on the go by backpropagation, you end up getting robust and well performing models as long as you ensure that they are not overfitting, because neural networks can overfit very easily. And it's not just in images, you can even use it on multimodal data like speech to text, speech to speech, text to speech systems. And probably all of you are using it in some form or the other, like with your Google Assistant or Alexa and so on. And the most important thing to remember is that scale drives deep learning models. So the more data you have, and also if your data is good quality, it's not just about big data, but also good data. If you have more data, neural networks act as universal function approximators. They can approximate any kind of a complex function, a complex nonlinear function for that matter. So nowadays, that's why we are getting bigger and more complex architectures like transformers and so on, which are actually trained on a huge amount of data. And because they are trained usually on generic tasks like language modeling, you can fine tune them to solve specific problems. And that's where harder problems like natural language processing, understanding, generation, and so on become at least like you will be able to tackle it. Let's say a few years back, it was very difficult to tackle these problems at scale. Nowadays, we have moved beyond models like LSTMs and so on to transformers, which are able to solve a lot of these problems with ease. You don't even have to write like hundreds of lines of code because it is more data driven rather than code driven. And the other reason why we are talking more about deep learning now is neural networks have been there since decades, but it's only in the last 4 to 5 years we are seeing that, of course, we are in the age of big data. We have a lot of data available to us usually. We are having faster compute finally in the form of GPUs, which can do matrix multiplications at scale parallelly. We are having probably the best open source software ecosystem right now in the form of TensorFlow, PyTorch, Scikit-learn, and people actively working on improving these software frameworks so that we can build the models with ease. And we are having the research community coming out with new types of models like residual networks, self-supervised learning methods, and so on. And that is why, because we are having the latest architectures, the latest and the best software, good data, more data, as well as faster compute, deep learning has really taken off in a lot of industries, and it is no longer like a theoretical subject being taught in universities and so on. And transfer learning is another reason for the success of deep learning. If you know how to perform a prior task, you should be able to solve a new task or do a new task by leveraging some concepts from that. Like if you know maths and statistics, you should be able to leverage those concepts to understand machine learning better. That's a given. So the concept of transfer learning is exactly the same. If you have a system which can very effectively understand how to classify different images, even if the images are of a completely different category, like vehicles or faces or animals. You can take that model and take its prior learned knowledge, which is basically the weights of the layers of the neural network, as we discussed, and you can adapt it to your own label data, even if you have less label data, like let's say predicting if a person has diabetes or not by checking a medical imaging scan. So in that case, you can adapt the weights of that model and fine tune it to solve your own problem. And often it gives you a superior performance than training a model from scratch, especially if you have less data. So that is the whole concept of transfer learning. Leverage the knowledge from prior learned tasks to apply it to solve problems in related domains. Like you can take an image classification model and reuse that model to do image classification, object detection, segmentation, and so on. The reason is because you can leverage a network which is very effective in extracting the right kind of features from the images automatically, right? Because we are not doing anything manually here. So that's the whole perspective of transfer learning. And there are a lot of universities, a lot of companies like Microsoft, Facebook, Google, and so on, who have built these models on a lot of data, doing the hard work. And instead of you training deep learning models from scratch, you can pick up some of these models, adapt it to your own problems, to either use it for feature extraction or use it for end-to-end tasks of building the model, training it, and then predicting something. And nowadays you have models available for computer vision. Like all of these models are state-of-the-art models for computer vision tasks on images or video. And you have NLP-based models also nowadays available. And this has especially taken off since 2018 with BERT and all those other transformer-based models coming into the forefront. In terms of deep learning model architectures, this slide probably covers the most popular models you will need to solve 90%, 80 to 90% of the problems in the industry. You have convolution neural networks, which you can use for images, video, audio, as well as text. So it is very diverse and versatile. You can use recurrent neural networks or its better variant, long short-term memory networks or gated recurrent units to process sequences of data and then predict, like, let's say, the next price or whether the price is going up or down, or even an outcome like the sentiment of a review by processing the words of the review in sequence. And you can capture better context by processing the sequence of data from front to back and back to front. And that gives us bidirectional models like bidirectional LSTMs. In case of unsupervised learning, you can use models like autoencoders to automatically learn useful representations from data. This is very useful in areas like anomaly detection, denoising an image to basically make it as a clean image, and also things like visual search, image similarity, and so on. And then you have encoder decoder models where you take in a sequence of data and generate another sequence of data. Most common application is language translation, where you can translate one language to another language. And obviously, I think almost all of us have heard about transformer models, which are all the craze recently, which is nothing but a stack of encoder decoder models with innovative concepts like self attention and multi headed attention, which can be used to solve diverse tasks in NLP like classification, summarization, sentiment analysis, question answering, and so on. Now, I'll briefly talk about some of the main problems. Well, not some of the main, but at least diverse problems in the industry in terms of relevance as well as practical uses. And the first one is about predicting data center device failures. So I will talk about just the essentials. We won't be diving too much into the project details, given obviously there are various NDAs on this, but you will be able to get the gist of how was deep learning effective and what is the problem all about. So predicting data center device failures, I think all of us know about data centers and network devices which are interconnected and are the key infrastructure in any kind of enterprise. Like we are on this Zoom call right now, and this call is being powered through a data center which belongs to Zoom. Let's say if that data center went down, probably all Zoom calls would get affected. So that's the whole point of it, that these are very key infrastructure components, and knowing when these devices can fail is very important. And a lot of these systems are reactive in nature, where the operations team works on these failures only after they have occurred. Like, for instance, recently, services in YouTube or Google or even WhatsApp, for that matter, went down. So it's actually very difficult to predict these beforehand. So this is where, for a particular domain, we try to see that can we leverage historical data around a few data centers to be able to predict the future failures of those devices with a good enough lead time. Like, can we predict 1 hour before, saying that based on the condition and the parameters of this device, probably it's going to fail in the next 1 hour? So that is one of the most important things, prediction before it happens, early prediction or early alerting. And that is where we had historical events data for different data centers, like, let's say, the number of connections which are coming in, which device is connecting to it, did a disk crash occur, did the CPU utilization go up, which applications are running right now, what information is being logged. So these are just some examples of device events which can happen in any kind of a data center device or a server. So what we did was we extracted windows of data from this time series data, where a bad observation window is, let's say, 6 hours worth of time series events data, at least 1 hour before a failure had occurred. So we take a 1 hour lead time before the failure occurred, and then go back 6 hours and we capture all these events to basically capture the state of that device before a failure occurred after that 1 hour lead time. And in between all these bad states of the device, we also captured 6 hours worth of data where before and after there were no failures in the horizon. So that's like 6 hours worth of events data for devices when it's operating in the good state. There are no issues. So in this way, we labeled our data. And of course, we had historical failures from the 2 years worth of historical data. And then the idea was to manually extract features from this, like the counts of the events, some kind of n-grams, like if event A, B, and C have occurred together, all these kind of aspects. But manual feature engineering and then machine learning was not leading us anywhere in terms of realistic performance of the model. So that is where we thought of transforming this events time series data into some kind of a heat map. And this heat map is where the time was binned into 5-minute intervals on the x-axis, and the y-axis consists of all types of events, which were, I think, over 40 events in total. So these are on the y-axis, and these values will be basically the number of times each of these events are occurring. So imagine the time series in each window is now a two-dimensional matrix or a tensor of events occurring in that 6-hour time slice. And essentially, this forms like a heat map of values showing the intensity of different events over time. So the idea is, why not let a CNN itself extract automated feature patterns from both good and bad windows to figure out from these heat maps when a device is going to fail versus not going to fail. And this is where this was one of the first convolution architectures we had used, with different convolution and pooling layers to extract features from matrices of events over time. And then we also experimented with deep transfer learning by feeding this into a pre-trained model, which is already an expert in distinguishing and extracting features from image-based data, because our events data is like a two-dimensional heat map, which is like an image, and predicting good or bad. So these are some high-level numbers which we obtained, where the critical event prediction rate is to predict when the failure might occur 1 hour in advance, and false positive rate is when our model predicted something, but that was not a good prediction. So reducing this is very important, and increasing this is very important. So these are real world numbers which you see in front of you. And you can see the struggle with manually extracted features. Of course, we don't say the features because of confidentiality clauses, but these were all manually extracted features trying out with shallow neural networks or machine learning based models, and the performance was nowhere near to what we obtained with deep learning. So this was one real world example of deep learning. Some other examples, again, given the interest of time, I will not go into too much detail, but as we all know, malaria detection is a very critical problem in tropical countries. And the process of detecting malaria is very manual intensive, where you have to take the blood smear, you have to magnify it. You need an expert to visualize that, and then they can say whether you have malaria or not. So the idea is, if we already have label data of blood smears, can we build an automated model which can take in that blood smear scan and predict whether a person has malaria or not? Our actual problem was more intensive in the form of image segmentation also, but here I'm just talking from an open perspective without diving into too much of those confidential details. So in this problem, as you can see, you have cells having malaria as well as healthy cells. This was data, again, which is even available in an open source format also. And this is real data open sourced by hospitals. And the idea was to build a convolution neural network to extract features and then build a classification system. And that is where the process or the workflow is very similar to most deep learning or machine learning problems. Split your data into training, validation, and test. Do some image augmentation if necessary, like cropping, rotation, contrast, adding some Gaussian noise to generate more data. And then try out different types of CNN models, like building your own CNN from scratch, or using a pre-trained CNN model, or fine-tuning a pre-trained CNN model by opening up all the layers and fine-tuning the weights as you train it on your own malaria data set, and then evaluate the model performance. So one of the popular models is a VGG19 model, which is a 19-layer deep learning model, which uses a bunch of convolution and pooling layers to automatically extract features from these images. And this model was trained by the visual geometry group at the University of Oxford to solve the ImageNet challenge. If you Google the ImageNet challenge, you will see that is a challenge where different companies and organizations compete to build the best deep learning model, which can train on millions of images and predict 1,000 different classes. So it's like 1,000 class classification problem. So it's like this model has already been trained on a lot of data, and it is an expert in extracting features from images. So all we do is we subset out the feature extraction part of this network. We don't care about the classification layers because we are not doing 1,000 class classification. We are classifying whether the person has malaria or not. So we extract out this part of the network. We add in our own classification model with two output neurons to predict malaria or not malaria. And then we train this model modified network on our data. And once we do that, we basically look at the training and the loss learning curves, and we see how is the accuracy over multiple epochs which the model trains on the same data. And then we observed that with a fine-tuned model where you opened up the layers to update the weights of the neurons also, as we discussed earlier on this data, you ended up getting a pretty high accuracy as well as F1 score on the test data also. So that kind of showed the promise of transfer learning, because precision is very important in these kind of models, especially in the case of healthcare. The other one was more around cybersecurity, where the whole idea is any of us, when we do a project, we don't code everything from scratch. We take some kind of libraries and then we try to build models on top of these libraries or build applications by using these libraries. Like, let's say you would use something like Flask and Python to build a API. You would not code the API like the API infrastructure methods from scratch. In the same way, if you're building something like a deep learning model on the cloud, we would probably use things like the Google Cloud libraries along with TensorFlow or Keras to build this kind of an application. You wouldn't code everything from scratch. So dependencies are all about open source third-party libraries, which all of us use to build software. And that is where, if you can see the dependency landscape, the number of unique libraries or new libraries which are coming out over time, third-party libraries like scikit-learn, pandas, TensorFlow, and so on in the context of Python, excuse me, you can see that it's huge. In case of the JavaScript ecosystem, that's your node ecosystem, you can see that the number of libraries are exponentially increasing over time. And similar kind of, you can see increase for other kinds of ecosystem like Java, Python, and so on. The problem with more libraries being released over the years is that the number of vulnerabilities in these libraries also increase over time. And a vulnerability is kind of like a weakness in that library, which malicious attackers like hackers can use to gain access. And I'm sure all of you have heard some kind of things like this on the news that, okay, this software has a serious vulnerability which can expose your system, or a man in the middle attack, or someone can gain access to your credit card information because this web page had this kind of a vulnerability. So that is where passwords being leaked and people gaining access of your system, ransomware, all these things are the effects because there are vulnerabilities in the application which has been built on top of these dependencies. And that is where our problem was more in the context of the Kubernetes ecosystem, which some of you may have heard about, which is used to scale applications. So our ecosystem was the Golang ecosystem. Golang is also programming language, and the whole Kubernetes and OpenShift suite of products, which are cloud-based products, which can help you in scaling your applications and maintaining them. So our idea was that these enterprise software systems are built on over 850 plus open source libraries. And if any of these libraries have a vulnerability, then that can be a problem. So can we know about it as soon as it is possible? And that is where we found out that a lot of public data is available because these are open source libraries. People are talking about them all the time on forums like GitHub or Bugzilla or other message boards. And what we did was we built an end-to-end architecture, which I won't go into too much detail given the interest of time. But briefly, we extracted public events from GitHub, from mailing lists, from Bugzilla, any kind of forums like Reddit, and we extracted all that text data, and then we try to pass it through some of our trained models like bidirectional LSTMs or BERT to figure out whether there was indeed a security vulnerability issue or not in this library based on what people are talking about it. And that is where we also leverage transformer models very recently because they were released around that time. And we got a superior performance by leveraging the BERT model. And the BERT base model, which consists of like a stacked 12 encoder layers, gave us a pretty decent performance. So the overall workflow for us was to regularly monitor 850 plus GitHub repositories as well as message boards and other forums, which are being used by the Kubernetes and OpenShift ecosystem, extract all kind of textual information like pull requests, discussions, commits, comments, conversations, and then pass it through the first model, which basically filters out any kind of comments or information which are not related to security talk. And the second model helps us in figuring out that are these people talking about a security issue or a security update or a security vulnerability. So this was the most important model, which helped us in getting to those insights. And we had security experts obviously refine a model because it is a real model. It does make mistakes. And we focused on last 3 years worth of data, and it was a highly imbalanced data because it is not like every day a library will face a security vulnerability issue. So we had over 200,000 relevant events of interest, and out of that only 650 were related to common vulnerabilities and exposures, which are like the true security issues. So you can see that the scale of imbalance was really high, but the deep learning models did perform pretty well here on this kind of a label data over the last 3 years. And this was the performance, as you can see. And these are real numbers in the industry where, if you see, we have a 99% performance to predict a non security issue as non security, which is great. But that is the level of accuracy which is expected because no one is going to reward you for this because it is expected your model should not flag too many non security issues as security issues. But the real test is this, where if you correctly identify a probable vulnerability, then that is a huge win for your company as well as the companies it is collaborating with. So that is where 80% recall and 71% precision, pretty decent numbers given the complexity of this problem using the BERT transformer model. The last two use cases before I wrap up is around vision-based problems, more in the context of generative deep learning, where you are not predicting class A or B or something, but you are generating a completely new image. So your prediction is like a complete new image which you're generating. And image super resolution is where you generate a visually pleasing high resolution image from, let's say, a very small low resolution image. And it has a lot of applications in case of image generation, medical imaging, where people may have a small scan which is not very good resolution. You can blow it up to 5 times or 4 times its size and resolution and still maintain a good quality of the image. So this is where it is used in security and surveillance imaging to, let's say, blow up security footage and see the license plate of a car, or blow up a medical imaging scan and maintain the resolution of the image. So this is where deep learning has seen a lot of advancements and success. And these are some of the state of the art models. Again, I won't go into too much in depth given they are like lectures on its own, but the whole idea here was to use residual deep learning networks along with generative adversarial networks to generate those visually like pleasing images with a high resolution. And the whole point here is, again, there is no secret or magic here. To train this model, you need supervised data, which means you need labeled data for the low resolution part of the image, and you need a corresponding high resolution version of the image. So let's say you have the image of a car, which is very low resolution. You also need that same image of a car in a high resolution, so that when you pass that X and Y to the model, it can learn the right kind of representations to blow up that image. So that is where, without label data, nothing is possible in this case. And it uses different kinds of loss functions, like obviously a signal to noise ratio, as well as passing the images through some deep learning models to extract useful features and then compare how close are those features. So using a combination of deep learning and transfer learning, you are able to get really visually pleasing images of a high quality. And this is where this is a popular network which is used, called residual in residual dense block, which uses multiple residual networks in each block and stacks them together to generate an image known as a super resolution image, and compare it with a high resolution image to see whether you are close to the ground truth or not. And this is like one of the examples where, if you have an image which is very small with not that great resolution, when you blow it up, it should retain all the visual aesthetics of the image and give you a high resolution image. And this is a popular application, as we discussed, called image super resolution. The last application, probably a lot of you have used this in some form of Photoshop software or some kind of applications on your phone, is stylizing an image, where it is called neural style transfer because it uses a deep neural network to superimpose the style of, let's say, some kind of a painting on any kind of a photograph, like in this case, the Taj Mahal. And this is an optimization problem which basically extracts the style components of an image, like the texture, the brightness, the contrast, the visual aspects, the color, and tries to superimpose it on the content image without degrading the content of the image, like the pillars, the dome, the water, and so on. So that is the whole point of neural style transfer. Given the interest of time, we won't be able to go too much into the technical details, but essentially what we use are convolution neural networks to extract features from both the style image and the content image. And we use usually pre-trained models like a VGG model, which we discussed even in the context of the malaria detection. So you can see that you can use the same model to solve different problems. And we use a pre-trained model like this to extract effective and efficient features from the style and the content image. And as you can see, once we extract these different components of style as well as the component of the content, we basically end up merging or superimposing them in such a way that we end up minimizing the loss. And then we end up generating, as you can see, a visually pleasing image where you incorporate the elements of the style onto the content image. So again, I know this was a whirlwind tour, but given that we have a short amount of time, hopefully this gives you a good perspective about what is deep learning, the motivation behind why you should know deep learning, as well as different applications in, as you already saw, diverse domains which have been solved using deep learning. And that's all from my side. Thank you.
All right, Dipanjan, thank you very much for that talk. Everyone, the goal or purpose of this session, that what Dipanjan spoke about, was to help you understand the context of deep learning and to help you see the possibilities of deep learning, if you're just starting off and if you're doing your machine, if you're right now in the first three terms, or if you're doing machine learning, don't get overwhelmed that how would I learn so many things, right? But the idea is to for you to see the end goal, what Dipanjan spoke about. Yeah. So Dipanjan, now we'll start with a barrage of questions. Yeah. So let me start with the first question, because Q&A is what I think is the most interesting part about any talk. So the first question is, you spoke about a very important fact that companies which have that advantage of data, right, have an unfair advantage. In fact, last year when I was in the US, I drove a Tesla for the first time. And I was so amazed. I was discussing about, about with someone about the future of Tesla from a stock perspective. And what he said was amazing, that don't look at Tesla as an electric vehicle company. It is an AI company. They are 3 or 4 years ahead in terms of the data that they are, that they have as compared to its competitors. Now, the question to you is that, does doing something like deep learning, which is the future, does it make companies monopolistic? Because smaller companies, normal organizations don't have that access to data, which companies like Google, Facebook, Tesla, and some others would. So I want to understand your perspective on this data monopoly and deep learning monopoly from an organizational perspective.
Yeah. So the truth is, data drives these things, and that is something which we can't stop. So definitely, these companies have an advantage, but so do companies which spend time collecting data. Like we have seen a lot of small-scale startups which work in things like, let's say, language translation, where they have painstakingly collected data. They have actually recorded data. They have gone to different places and got this data, and they have built their models. And the models are nothing too difficult, because nowadays you have the latest state of the art models out there. But the secret behind a lot of this is data. So it is definitely true that the larger corporations have all the time, resources, and money to do this. But we are also seeing small scale startups being able to do this. And then because the large companies see that these startups have done so well, they end up acquiring those startups. So they would never have done that if they wouldn't have seen the potential. So from a deep learning perspective, yes, without data, nothing is possible. But doesn't mean you can't build good products even if you don't have a lot of data. Nowadays, we are seeing that is why this advantage of unsupervised learning as well as transfer learning, which is enabling us to solve a lot of problems with ease. And that is where we are seeing open source initiatives also, like the whole Transformers open source initiative from Hugging Face, where they are even running competitions on open source data, and you are able to get state of the art models which are actually being used inside companies. So I think from that perspective, these are some models which can help us tackle that data gap of not having too much data. But the other perspective is, yes, to build something successful, ultimately you definitely need data. Ultimately you need good quality data, not just a lot of data. So these are a few things which are very important. And rightly, to your thing also, like you said about the Tesla aspect, where they are collecting so much data from all these cars. It's like a fully connected system, and that is how they're able to generate better levels of autonomy in the future, where they are going for that fully autonomous system, right? So without data, nothing is possible if you just have a car. So that is why we are seeing all these smart systems being built where everything is sending out data. And that is why we are also seeing things like AI on the edge, where you have these IoT devices where you are trying to push the model so that it can learn from the data there itself. So yeah, I mean, you definitely need these things to build good products.
All right. So follow-up question on that is, let's say if I am a tech lead working in a bank, yeah, and I want to work on deep learning models, and I am serving a Fortune 500 client. Now, how should I go about? Now, the problem with most of the banks is that they have a lot of data, but there's a lot of issues related to data privacy and all. And the clients are usually not very open to sharing such huge amounts of data. They would give you some small data if you want to do some prototype, etc. But if you really want to build a deep learning model, that you'll have to go through layers and layers and layers. So how would you recommend, let's say, if an Insaid student working in one of the big companies wants to approach the client what should be the pitch, because it's as much about persuasion, as much about showing the vision, as much as it is about actually doing deep learning.
Got it. So the strategy should be same like we do with almost any project. You have to start with showing some numbers, and then you have to pitch the promise of where you can get and where you may not get if you don't explore the possibilities. So in banks, again, I would be a bit apprehensive about going for deep learning right away. So my approach would be the same as we do with most projects. Start off simple with effective techniques like simple logistic regression or maybe some tree-based models which are interpretable to an extent. Showcase the kind of performance you're getting on the given data, and then showcase that if this is the level of your performance from X and you want to reach to 10X, then what do you need to do to get there? And talk about methods which automatically learn from data, which can basically give you a better performance as they get more data, and also which can automatically learn on the fly without you having to spend excessive time in development. So basically, that pitch about time which would be less involving from a development perspective, as well as showcasing the promise of superior performance. Those are the key things. The other thing which companies like, I know for a fact Citibank and American Express have been exploring is, with that less data, they are trying to feed it to models like generative adversarial networks to generate more data and then check performance. So that is another approach which you can always do, where you can try and generate more data till the time, let's say, you are selling your pitch and basically gaining more access to the data or them being more open to things. Yeah.
Yeah. So the summary, everyone, is again the concept basics remain the same. Start with something small, show it to the client, and then scale it from there instead of directly asking for something which is very big. So I think that proof of concept still remains an important point. Yeah.
Yeah, you have to show the value for sure before you can ask for something humongous, right? Because you don't know whether deep learning will give you really that level, which you haven't even seen with any kind of baseline model. So, yeah.
Right. So, Dipanjan, my next question is, and after that, I'll open it up for everyone to ask their questions in the chat window, is that with OpenAI launching GPT-3, it promised a whole new world of abstraction of AI. Right now, when it comes to deep learning, you have to learn a lot of calculus, you have to learn a lot of things, right? Which possibly for, I mean, the whole idea is that can we get to a model wherein things are so abstracted that a normal person can also start using something like deep learning. And with GPT-3 and the APIs that it makes accessible, I want to understand that where do you see this entire field going towards? That do you see more abstraction happening, and do you see people using plug and play of deep learning models, something like GPT-3, or do you see we'll continue to use more of deep learning in the way we currently are?
Sure, this is very good and relevant. So the main thing to remember here is, one, we are going to definitely see more and more low code interfaces coming up in the context of automated machine learning. And that is something I would recommend everyone to embrace openly, because it is not something which is making the data science extinct, as a lot of hyped up news articles may show, but it is something which augments the data scientist, where you can quickly explore a wide variety of models to get to something which works out well, and then tune that to solve real world problems. In the context of GPT-3, just remember this, that it is an API. You don't know what is happening behind the scenes. Plus, it is not cheap. It is going to be very expensive if you want to fine tune that model, as is the case with any kind of deep learning model as a service. Like, you have deep learning models being available as a service through Google Cloud, through AWS. It is like free to use for a couple of seconds, maybe. But as soon as you push your data, it is very expensive and it's charged per hour. So even large scale multinational corporations don't invest in that unless they know it's a sure shot success. So that is where open source is still going to be pretty big. And your in depth knowledge of deep learning and machine learning is going to be very important, because unless the company has thousands of dollars to shell to use these services, it is going to be very difficult. And the same with all these startups which are coming out, which are built on top of GPT-3, because for them, they are not getting access to the model architecture. They are just using it as a service. Now, as long as you have the right kind of data and you are very sure that, okay, this is my input and this is the kind of output I will be serving, and that is consistent, you're good. But the challenges with a black box system is you never know when things can change because of data issues, model drift, concept drift, and so on. And you can't retrain the model as effectively as having the full white box knowledge of the model. So a lot of the startups could someday just die out because they are not being able to get the output they expect. So if you know for sure what are your inputs and outputs, you can build some great startups on top of GPT-3. But the biggest challenge with these kind of models is the control. You don't have as much control as you think you need. So I think it will be a long time still before we get to that level where everything is API driven. And also from a practical cost perspective, 99% of companies, including Fortune 500 companies, won't just jump into the GPT bandwagon because, I mean, they have a budget at the end of the day. And unless they know for sure it's working out, they will not invest in it. Yeah.
All right, great. So let's open it up for Q&A. Everyone, if you have questions, just keep your questions a little short, and then I'll start taking your questions, and we'll request Dipanjan to field some of them. Yeah. So Dipanjan, one question is from one of our very active students is Lalit Garg. I am from retail industry and would like to understand more use cases of deep learning in retail. If you can please elaborate.
Sure. So in retail, I think one of the first things which we are seeing is around recommendation systems. So traditional recommendation systems are based on matrix factorization and are based on techniques like singular value decomposition and so on. But the problem with those are they usually work on a lot of sparse data and high dimensional data. And nowadays, everything is becoming concept driven or embedding driven, if I want to become very technical. So that is where we are seeing the hybrid recommendation systems, where it is all about representation learning and building end-to-end systems which are more personalized based on deep learning systems. So definitely we have recommendation systems. And then a lot of innovative applications, like I said, stock out. So we are having these shelves which are being monitored by computer vision based systems, and they can figure out when something is automatically going out of stock. So that is a full-fledged application of deep learning for computer vision, as well as compliance in terms of product placement, as well as brand placement. Companies like Coke want to know whether by chance a company like Pepsi or whatever, they have a product just beside the Coke, because they will often have agreements with retail stores that you shouldn't be doing that, and they may even have contract for that, and these are like sometimes $1 million contracts. So they are having these kind of systems where they can see where exactly the logo is placed, what is the logo, what is the distance from the product, those kind of systems. And we are actually seeing startups who are actually building these kind of products, and large multinational corporations are tying up with these kind of startups. So these are innovative applications of deep learning in the context of retail. Other than that, it really depends, like personalized search. So when you're searching for something, sometimes you may want to just take an image and see similar products. Sometimes you may want to type a description which is very vague and still see relevant things coming up in the search. So I think multi-modality search powered by, let's say, sometimes speech or text or different kinds of images, combining them, deep learning is the way to go, because traditional search-based systems nowadays have mostly been replaced, even like simple Google search. So yeah, these are some things which come to my mind right now.
Great. I think Parimal has a question. Parimal has this question like auto ML, is there any possibility of auto deep learning? Parimal, quick answer to that is it's already in the work. If you look at Google libraries like Auto Vision, Auto NLP, it's already there, that where you don't have to do a lot of the work. You use the platform and you start building deep learning models, right? So that's the answer to Parimal, your question. Now, the next question, Dipanjan, is that when it comes to branding yourself to become successful in this space, a lot of our students are wanting to get into the space. What are some of the things that you have done to stand out? You are among one of the top 10 data scientists. You've been ranked among one of the top 10 data scientists in India. You have been ranked one of the 40 under 40 data scientists in India, etc. So tell us a little bit about how to brand yourself, because that's, I believe, is a very important part that can really give you that push in terms of being seen by the right recruiters as well. A lot of our students, for example, somebody, Ankita asked in the chat window, is that how do I get into a company like Google? Or Google is just an example, it could be many companies. So can you talk a little bit about that?
Sure. Yeah, maybe I can take a full session on this because I
Yeah.
recently did that also in terms of how can you build a profile for yourself and even talked about my own journey. So the short answer for this is showcase yourself in ways in which people can know you. So that means do end-to-end projects, and this can even be small scale projects. It is not like you have to do a super complicated project. Let me tell you, 70% of problems in the industry are not like huge problems which take months or years to solve. Sometimes it can even take weeks. And the same techniques you are learning in your course is what you will be applying also to solve these problems. So start off by building a portfolio of projects in different domains. Like you can do fraud detection, you can do churn analysis, but market those projects in the right way. Write a GitHub README, maybe do a short video on them, or publish a bit about it on Medium or a blogging platform. Because in that way, when someone else will be searching for those kind of keywords, your things will come up to an extent. The other thing is, if you do something end to end, talk about it somewhere, go to a meetup, talk about your project. In the long term, go to a conference. When I started out by attending conferences as an attendee. It's not like from day one I was a, let's say, top data scientist, though I would still personally say I am still a long way from being top. But again, coming back to reality, I attended a lot of events just as an attendee because I wanted to learn and listen from other experts in the domain. So that is what you should be doing to learn, okay, what is happening around me. And then you start sharing your knowledge, because even if you go to a meetup, sometimes a lot of influential people will also go out there and network with them. Nowadays everything is happening through Zoom, which is fine, but still try and connect with people in terms of virtual events, conferences, in-person events. Start sharing your knowledge in the form of webinars, in meetups, because in that way more people will get to know about you. And you can do other things, like if you have a lot of information collected, you can publish a book like I have done. So I would say self-publishing is also a great way to go. You don't always need to publish with a brand. Honestly, there are a lot of restrictions. In that way, I have seen there are a lot of top books on Amazon which have been self-published by people. And when you are publishing, basically I'm not publishing for money, but I'm publishing because I want to share my knowledge. So in this way, if you share your knowledge with the community, you build up projects for yourself, tangible artifacts which people can see, publish a research paper. These are ways in which you can slowly build up yourself and start getting noticed, definitely. And as long as you are consistent in terms of what you talk about, you are genuine in what you talk about, because we have seen people who try to mask things or try to like show off and all these things, and it may work initially with some flashy things, but somewhere down the line it may backfire if they are not genuine. So as long as you're genuine and you have good content to share, people will come and consume that content. And in that way, another way is if you contribute in some kind of open source projects, you can get directly noticed by companies. So as long as you're doing all this, I think it's a great way to build yourself up, and it will be beneficial in the long term, because it has not just worked for me, but a lot of other people. And some other areas are like participating in Kaggle competitions or competitive ways to continuously push out ways in which you can market yourself. Yeah.
Great, great answer. And everyone, did this answer help? Because that's one of the things that we keep on asking all of you, that it is not just about learning. So give me a quick yes in the chat window if this is super, 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 super important, right? So please understand this, that there's no point in doing 100 different things and 100 different courses. But what is really important, as Dipanjan said, is that if you're learning something, just try to let people know. It can be through GitHub, it can be through a simple post, and you don't have to ever think that who am I? I'm not even expert. That's okay. But you have invested 4 hours working on a project. Can you take out 1 more hour in writing an article on that? And that's fine if nobody reads that article in the initial go. Yeah, but over a period of time, you'll have a solid repo of articles with you that you can, somebody, if you say that I'm an expert in this, somebody will at least give you an opportunity because you have showcased that. And that's something, Dipanjan, is very important, because you would see that right now the trend is that a lot of people are doing courses, but not talking about, not marketing themselves, which is so very important. So help us understand that as a learner, how do I balance between learning, yeah, and sharing, right? What should be the right proportion for me in terms of doing this?
Absolutely.
So the question to you is that what is the right proportion for learning and, let's say, sharing about or talking about the things, or publishing the things that
Got it.
I'm doing?
So this is something I want to say, even from the context of not just data science. If you see the startup ecosystem in India as well as in other countries, one of the key things, which I think now we are doing better, especially Bangalore and other startup hubs, is that if you see a lot of the startups which are not in India, they do a great job of talking about it. But from
Absolutely.
our perspective, we are very technically sound, but we sometimes don't talk about it as much due to different apprehensions, like, okay, am I as good as others, or those kind of things. So don't worry about all these things. And this way of sharing things is not just for the sake of sharing. When you are in a company, if you don't talk about what you have done in the right way, you will slowly start yourself basically in the way that you will not be that prominent. You will be maybe someone who is behind the code, but if you don't talk about these things, then you will not be there to get that promotion which you want, or to get to that next level which you want. So from that perspective, talking about what you're doing is very important, and nothing to worry about what are others going to think of me. As long as you have done something relevant, it's okay to make mistakes, just like we discussed right now, right? So the main thing is you will learn over time, but don't hesitate in sharing what you have been doing. But that is where, again, the balance should be such that you learn and you share. You don't just start sharing something without having enough knowledge about it. And we have seen this happening in a lot of places, where a lot of prominent people, just to gain some limelight, try to bring out something which is very cutting edge. But if they don't say what it is from a, let's say, ground up view, in terms of what is this technology, or how will you really use it, or what is working behind the scenes, then people will call out them, like, obviously, that, okay, you don't really know what you're talking about. So from that perspective, as long as you know what you have done, and as long as you have done that background research about what you have done, you are more than ready to start sharing your content. And in that way, like I said, start off small, maybe share with the people you know, which could be, let's say, a cohort with which you're learning. Share with them, learn from your mistakes, and then you can share in a widespread platform. I'm not saying that go and start making a YouTube video on this, where millions of people will come and tell that, okay, what are you doing? This is not right. Once you validate things on a small scale, you can then go in a larger scale. So the main thing, again, coming back to the question, is that you should know enough before you start sharing. And that is the most important thing to keep in mind regarding any new technique, technology, a project, whatever be it.
Okay, great answer, Dipanjan. And with that answer, let me give an assignment to everyone. Everyone, can you take up this assignment that in the next 1 month, can you do a presentation in your or own organization on any topic that you feel passionate about, whether it is data visualization, data analysis, machine learning, and deep learning? Can I get a yes for that? Next 1 month, one topic that you feel passionate about, because I'm sure 90% of us here would not have done that. We are doing the program at Insaid, but we are not even sharing with our colleagues. So it could be just a Zoom meeting that you are having with a team, wherein you ask a manager, can I talk a little bit about, data analysis? Yeah. So in the next 1 month, can you all do that? Because that is the first step where you'll go out of your comfort zone. You'll hesitate a little bit, but that's fine, right? That's the first thing. Yeah. So I think, that would be a very good starting point. Yeah. All right. Two last questions, Dipanjan. The next question is that how should I go about thinking about deep learning, and at what point should I go about thinking about deep learning. Should I start thinking about getting into deep learning once I have gotten into machine learning and gotten a job as a machine learning engineer or a data scientist, etc.? Or can I skip all of these steps and realize that deep learning is my calling and start looking at deep learning as a field and start applying for roles directly into computer vision, wherein some of the recruiters might question me as a candidate? For example, they would say that, oh, you have never worked as a data scientist. Can we trust you whether you will be able to do computer vision? So do you see it as a step-by-step journey in terms of not only learning, but in terms of job progression as well? Or do you see that a jump is possible where someone who's interested in deep learning and applying these techniques can directly move from learning to actually getting a job in this field?
Sure, sure. So the main thing is in terms of learning, one thing is for sure you should know enough machine learning before you go into deep learning. I have seen some people go into deep learning and the way they have gotten about it is a bit, I would say, wrong, where I keep getting these messages or emails or whatever that okay, I'm trying to solve this problem. I have applied all possible models. I don't know what is happening. So that is basically going to happen if you don't know the fundamentals of what is a loss function, how do you look at validation metrics, how do you do validation in your model, when do you know that okay, you should stop training your model. And to know all this, you should know it from first a machine learning perspective. So once you know enough machine learning in terms of supervised learning and unsupervised learning, I think that is a good enough foundation to dive into deep learning. In terms of job prospects, if it was a few years back, I would have told it's good to work a couple of years as a data scientist and then go for deep learning jobs. Nowadays, I have seen a lot of people who have basically studied machine learning and then dived into deep learning, done different kinds of projects. And let's say, like you said, someone found their calling in computer vision. They have specialized in different projects like computer vision, object detection, segmentation, image processing, classification, all those things. And as long as they have a portfolio of projects, that is what sometimes matters to these recruiters, where if you can talk about what you have done and you can showcase your skills to that level which they need for these jobs, you don't need to work initially as a data scientist in traditional problems for a couple of years and then only go to deep learning. As soon as you know enough machine learning, you can start diving into deep learning, because in that way you can broaden your scope also when you want to go for these jobs. So that is one important thing to keep in mind. And the other thing I also want to say is, if you know for sure you want to do computer vision or let's say deep learning on NLP and all that, and you know for sure these are the companies you're targeting, that is great. But if you're someone who doesn't know where you are going to apply yet, or the which jobs are going to be there when you are, let's say, ready to apply for jobs, I would definitely say invest enough time in machine learning and then only deep learning, because it's not like there are so many deep learning jobs out there, because deep learning is not something which will be applied in every company yet. It is getting there, but you need right problems to solve deep learning also. So from that perspective, don't ignore machine learning to do deep learning. But once you know machine learning, if you do deep learning, you can stand out as a person who knows different things.
Fantastic. Thank you, Dipanjan, for doing this wonderful session. I hope
Yeah.
you would have enjoyed doing the session and hosting, fielding these questions as much as we have enjoyed listening to you. Thank you so much. Uh, if the students want to follow you, how do they follow you, and where can they connect with you?
Sure. So you can usually connect with me on LinkedIn. I do keep sharing content from time to time. So maybe I will just post my LinkedIn link in the chat, and feel free to reach out to me. Of course, I do get a lot of messages, but if I'm posting something, feel free to comment on it, or you can even send me a message. Whenever I get time, I will always get back to you. And yeah, I'm usually active on LinkedIn, so you can always reach out to me there.
All right. Thank you, Dipanjan, for being here. Can we all uh, give applauses to Dipanjan for spending his time and sharing such wonderful insights with us? This was one of the best sessions that we have, done, and we would want to just express our gratitude for being here for this session. Thank you, Dipanjan,
Yeah,
for
thanks a
being.
lot, everyone, for all your kind messages. And Manav, thanks a lot. I think, yeah, questions were indeed amazing. And yeah, I mean, I definitely liked sharing my knowledge here, we'll be glad to come back again sometime.
Sure. Thank you, Dipanjan. A quick heads up, everyone. The Data Detective Challenge is going to happen in the last week of this month, last Sunday. I hope all of you have received notifications about that, and I hope all of you are preparing for that. As Dipanjan also had mentioned, and we keep on mentioning, going beyond what you're learning in the classroom and being recognized is very, very important. We had the Python Grandmaster Challenge last month. Make sure that the Data Detective Challenge is something that you are definitely participating in. Yeah. Thank you, everyone, and have an amazing Sunday. Bye bye. Thank you, Dipanjan. We can
Thanks
drop
a
off.
lot, everyone. Yeah.
Bye bye.